I'm Phil Koopman, and I'll be talking about an introduction to embedded safety engineering. In this talk, I'll cover the big picture overview of safety engineering, why testing does not make you safe, hazard and risk analysis, redundancy management, and safety culture. By the time we're done, you'll have the big picture overview of what safety engineering is and how you go about it. Let's start with embedded system safety scope. Traditional safety critical systems we all think of are things like aviation and rail and automotive and space. These are things that require a lot of engineering effort. The modern ones have lots of computers in them, huge teams, lots of process, and all those sorts of things. There are also some other things on that scale that are less commonly discussed, but when I say them, you'll recognize them. There's chemical process, there's medical, there's nuclear power. All these things have a lot of computers in them, and they tend to be safety critical. And it makes sense that you spend a lot of money and time and effort engineering them to make sure bad things don't happen. But there's a lot more to embedded system safety than the high-profile, spectacular projects. There's things like water, sewer, gas, electrical power, emergency 911 services. There's consumer appliances, battery charging, climate control, food safety, baby care. Those all have a lot to do with safety, and their computers doing a lot of those types of things now. And there's critical cloud-hosted features, things like navigation maps and maintenance procedures and over-the-air updates and medical dispatch. Over time, things have gotten increasingly safety critical. In most embedded systems these days probably have something to do with safety, although not necessarily as big a deal as an aircraft falling out of the sky. Safety's in there somewhere. So it's important for embedded system engineers to have an idea what safety is, how you go about it, and realizing that there are ways to get to safety that are less cumbersome and less onerous than what you might do for an aircraft flight control system, for example. Let's start with some common safety myths. These myths just keep coming back no matter what you do to say, oh no, that's not really true. You turn around and somebody's saying the same thing again. So let me shoot down some of the myths at the beginning, and then I'll follow up by telling you what safety really is about. One myth is that testing alone proves safety. People say, how do you know you're safe? Well, we tested it. Well, testing has never proved anything of any complexity was safe. It's a piece of safety engineering to be sure, but testing is not going to prove you're safe alone. And I'll come back and I'll revisit all these myths as we go. The next one is that safety is a compliance exercise. Safety, some folks will say, is, well, you fill out all the paperwork and the standards, and if you can use a photocopy machine or a printer to just replicate it, that makes it easier because it's just about the paperwork. That has nothing to do with getting safety. Yes, there's paperwork involved in safety, especially the more rigorous amounts, but the paperwork is not the point. The point is the paperwork documenting that the right thing, the process was done. And some people say that following a particular coding standard like MISRA C makes you safe. How do you know you're safe? Well, we followed MISRA C. Well, again, that's a piece of safety for many applications, but that alone does not get you to safety. People will say safety is just good system engineering. Oh, we're smart, so we're going to get safety right. Well, you may be smart, but if you're not following a safety engineering process, you will probably miss things. So it's more than just being smart. There's actually a methodical way that anyone can do safety engineering if they know how to do it. That's what we're here to discuss. And finally, you see a lot of deflections of safety concerns. Things like, well, you can't be perfect, so there's no point trying. Now, when I say it that way, it sounds sort of silly, but you hear variations on that are more subtle all the time. Well, we can't solve that problem, so there's no point in doing an 80% good enough solution. That's not true. You can always do something, and the question is not whether you're perfect. The question is whether you're good enough to have acceptable safety. Also, people ignore careless harm now because we're going to save lives in the future. Oh, never mind that crash. We're busy saving lives here. Stop getting in our way. You're costing lives by stopping us from being reckless and careless when we're on our way to someday saving lives, maybe, but we're going to see how that turns out. So those are rhetorical devices that people use to deflect safety, but you don't have to do that. You should just do safety engineering, and it's really not that painful if you have a product that's only a little bit safety critical. Let's get on to that. Let's work through that list, and we'll start by shooting down the myth that testing gives you safety. Testing has never gotten anyone safety for a complex system. Let's take cars as an example. If you're going to build a robotaxi or something like that, a good, very round number for the US over a number of years, depending on whatever, ends up at 1 fatality per 100 million miles in the US. Okay, so 1 fatality per 100 million miles, that's human drivers, including all the drunk drivers. Humans are actually pretty good at avoiding fatalities. They have a lot of crashes, but there are very few fatalities. And some of that is people are good at responding to bad events and avoiding a crash. Some of it is we have airbags, we have seatbelts, but it all piles up. That's the number. Okay, so you say you want to test. We're going to test our robotaxi to prove it's safer than the human. Well, to do that with any statistical significance, you're going to have to run 300 million miles to 1 billion miles of testing, depending how lucky or unlucky you get. Well, what are you going to do? Build a fleet of 1 million cars and run them around and see how many crash and then put them on public roads, put people on them? That's ridiculous. You can't do that. And no one would even think of doing that for an airplane. You're going to fly airplanes around for 1 billion hours without passengers before you put a passenger in? That's ridiculous. That's not how you do safety. Now, testing matters, but testing is there for a particular reason we'll come back to. Another one is debugging does not give safety. Okay, we're going to put this system out, and if something goes wrong, we'll fix it and wait, and if something goes wrong, we'll fix it, and so on. And there are two problems. So that one is it's doing harm every time something goes wrong that you should have prevented. And again, you can't be perfect, but you should do pretty well. You should be good enough, which is what we're here to talk about. But we all know that if you debug one bug, oh, yeah, we found a bug. For sure, that's the last bug. Well, that's nonsense. How many bugs are left after you delete a bug? All of them. Who knows how many? And in fact, the more bugs you've removed, the higher the probability is that there's a bunch more, because if you're dealing with low-quality software, debugging is never going to make it safe. It's just going to make low-quality software less buggy. So you need to do something else. Now, you want to do continuous improvement? Absolutely. If you find a bug, you should fix it. But the point is not finding the bug and fixing it. The point is, how do you have an engineering process robust enough that on the very first day your product is launched, you have a reasonable expectation of safety, and of course you want to get better after that. The reality is safety has to be designed in from the start of the project. You cannot add safety on at the end. That does not work. You need to start at the beginning and run a safety engineering process in parallel with your design engineering process. And we do that. We have a safety engineering process, and that's what I'm here to explain. Now, before people worry that I'm here to go through yet another safety standard and explain all the clauses and all the nuances, that is not what we're here to do. The point of this talk is to give you a very straightforward, very simplistic example of how safety gets done that you can generalize from. And we're going to start with a hypothetical application example. So here's a person holding a nail, and there's a hammer, and there's a wood fence, and this wood fence, I'm guessing, has gotten old and the nails have all worked themselves loose and it has to be re-nailed. I've personally done this project. My plan involved purchasing an air compressor, a pneumatic staple gun, and for a large part of it, hiring a teenager to do the work. But we're going to go a little bit different way on this, okay? Because it's the modern era. We're going to send in the droids, okay? We're going to have a robot hammer. We're going to give a robot a hammer and tell the robot to whack the nail in for us. Now, this robot doesn't have good dexterity. I mean, look at those claws. He's not going to be able to hold the nail. So our plan is I'm going to hold the nail, and the robot is going to swing the hammer for the first stroke, and then I'm going to remove my hands, and the robot's going to nail it in all the way. Now, some of you, especially those of you who've played with robots, know that this is maybe not the best idea in the world. But what we're here to do is use it as an example that obviously has some risks, so we can go through and say, here's a safety engineering process for this hypothetical example. Of course, it's simplified, but the point is to get the ideas across, all right? So the robot uses the hammer. A human hand holds the nail for the first blow, and then the hand is removed. So let's go through and how would you build that if you're trying to build it? Well, the only reason to build a robot to do this is because it's going to be accurate, it's going to be fast, it's not going to get bored, tired, distracted, whatever. And we got that human holding the nail. We'll come back to that, okay? But for the robot, you want to make sure striking accuracy. You don't want to miss the nail. Obviously, you're not going to nail it in unless you hit the nail. So I'm just picking arbitrary numbers here. We're going to build a robot so that it always strikes the nail within 2 millimeters from the center of the hammerhead. Maybe it's 3, maybe it's 1. I just picked 2 as an example. And the first strike depth, you probably want to go down 5 to 10 millimeters on the first strike to get the nail really set so the person can remove their hand and the nail's not going anywhere, and then the robot can beat it in the rest of the way. And the final strike depth, you want no more than 0.5 millimeter sticking up out of the fence. It's a rough cut fence, 0.5 millimeter is going to be fine, but you don't want to be putting big dents in the fence and you don't want the nail sticking out. So if you were building a product, what you might say is, sure, these are my performance requirements. I'm sure there are much more, but these are just examples. These are my performance requirements. If you can program a robot to do this, I'll be happy. And most engineers and most STEM folks, when they've been to school and most projects they work on, especially early in their career there, what they do is they get told, here's the performance metrics, meet the performance metrics, and we'll move on. When you're building something where safety is no big deal, sure, this is what you should be concentrating on. But now safety is showing up everywhere, so we need to ask the safety questions, okay? Safety engineering is a little different. Typical engineers optimize metrics and things you're going to ask, like how many nails per hour and how many bent nails because we're worried about waste and rework. But that's about it, all right? It's mostly about how fast can you go. And engineers just love to optimize. That's what they're taught in school, and that's great. But safety engineering is optimizing something a little different. Safety asks, what about when something goes wrong? All right, yeah, on the nominal case, you're pounding those nails and that's great, but something will eventually go wrong. The question is, what is it and how do you manage that? An important insight here is there's a lot more ways for things to go wrong than go right. Ask yourself, there's only so many ways to hammer in a nail in successfully, but how many ways can it go wrong? Lots of ways. And when you get down to a particular list, but I'm sure you can add 10x to the list. Those of you who've done a lot of hammering, probably from personal experience, all right? There's lots of ways for this to go wrong. And so safety engineering at its core is about identifying hazards. A hazard is something that can go wrong. So safety engineer, you start by saying, here's a list of the hazards. Here's the things that can go wrong. And you attain safety by saying that each hazard presents a risk, and you have successfully mitigated the risks from the hazards. That's it. Safety engineering in a nutshell. A hazard is something that can go wrong, and you get acceptable safety when all the hazards have been mitigated enough, not for perfection, but mitigated enough that the resulting risk that's presented by the system is acceptably low. That's it. That's safety. So how do we do that? Well, the first step is hazard identification. You identify the hazards, and there are two types of hazards usually. And again, this process is the simple version to get the ideas across. The first thing you do is you identify the failure mechanisms. Well, there's a lot of ways things can break or not work as expected, but you also identify usage hazards and operational limitations. Okay, some examples. Your hand is in a dangerous position, but if you put your hand over top of the nail, that's a bad thing, right? Or maybe the person forgot to put a nail, or maybe the nail drops out of their hand as the hammer's in motion, right? So those are hazards that can result in a bad thing. They're probably going to result in the hammer hitting your hand unless you do something special to prevent that. But we're not there yet. Just identify that things can go wrong. The hammer could slip and fly away, or the hammer could break, or the strike could be a little bit too deep and smash the fingers anyway. You could have an environmental limitation, like this thing wasn't designed to work in the rain and all the friction dynamics change when things are wet. Who knows what can happen? Maybe the steel shatters if the temperatures are too low. There's all sorts of limitations you have to think of, and some of them are a big deal, some of them are a little deal. But the first step in safety engineering is go through the entire list of things that can go wrong and then decide what to do about them. The decide what to do about them starts with risk analysis. Each hazard presents some sort of risk, and you decide what the risk is. Now you can go mathematical with this, but it gets really cumbersome. You can say the risk is the frequency or probability, take your pick, but it's the frequency times severity. So if you have something that happens all the time and it's a really high amount of damage, that's going to be high risk. If you have something that happens almost never and it's really no big deal, then that's low risk, and things in between. Now you can run this as a numeric exercise, and in some areas they actually do try and assign numbers to all these things. But for most practical purposes, it takes a lot of effort to come up with the numbers, and you're probably just guessing anyway. So to make this practical for most safety engineering, you do not try and get precise numbers for everything. What you do is you come up with a risk table and you bin them. And this is a super simple risk table. We'll go back to how they get more complicated. But for now, we're going to take every hazard and bin it as low severity or high severity. That's it. Either someone makes a trip to the emergency room or it's no big deal, okay? And then We're going to have low frequency, high frequency. We think it will happen often, or we think it will happen very infrequently. And from there, we populate the risk table. So these are the entry points, the severity and frequency, and then we assign a risk of high, medium, low. So if you have high frequency and high severity, that's going to be high risk. High risk, this does not mean the system will do that in operation. What it means is if you take no effort at all in safety engineering, you're going to end up with a thing that will happen all the time that will be very severe. And so that's high risk. We're going to get to what you do about high risk in a minute, but this is in the system as engineered with no safety engineering. Where do you end up? Low frequency, low severity, well, that's low risk, all right? Low severity, high frequency is medium risk, okay? Now, this is the tricky part. High severity, low frequency is not medium risk. It's really hard, and we'll have a slide later on that goes into why that's the case. So we're going to revisit that as we go, but for now, just take my word for it that that's a controversial question mark, and we'll go on. In practice, these tables may have up to like 6 rows and columns, and we'll revisit that, but this is enough to get the ideas across. Okay, let's do an example risk analysis. So we need to determine the risk for each hazard, and so we take the frequency and we take the severity, and from that we determine a risk by using a risk table. Let's just pick a couple examples for this hammer and nail. We have the nail goes too deep. It's low frequency and low severity. Now, I don't mean smashes all the way in. I mean just a little bit too deep, because maybe we wanted it to go in 5 to 10 millimeters and it goes in 15 millimeters. Why would that happen? It could happen because the piece of wood is old and it's a little bit softer, and the hammer presses with a constant force and doesn't realize that it's slamming a nail into a piece of rotted wood. But as long as we don't think the nail's going to go all the way down, we may say, well, it may bump your hands, but it's not going to smash your fingers completely. And there probably aren't that many rotten boards. We've done a survey. We've looked at a bunch of fences, and most boards are pretty solid. So let's just say this is low frequency and low severity, and that means it's low risk per our risk table. It doesn't mean we do nothing, but this is not going to send someone to the hospital. The next one is miss nail. And let's say that we've decided that's high frequency. We found out our robot has a lot of trouble getting the accuracy to actually hit the nail right on the middle of the head, and the hammer slides off or it misses the nail pretty frequently. We did some experiments and it turns out to be really hard to do that. And that's going to be high severity, because if the hammer misses the nail, the full force of the hammer is going to slam into the fingers. Yeah, that's not a good thing. So let's say that's high risk. We're going to have to do something about that. And no nail. Well, let's say in practice we used our professional carpenters and they always had a nail there. And so we've said it's low frequency, but it's high severity. And so even though we think it won't happen, maybe there's something that we haven't thought about, like in my case, hiring a teenager who wasn't that experienced at nailing. Maybe there's things we haven't thought about that would make the frequency just a guess instead of right. And so it's high severity. So it's not as clear what to do about that. So we're going to leave that as a question mark, and again, we'll come back to that. The next step is risk mitigation. We're going to mitigate each risk to achieve safety. So we did hazard analysis, we figured out what the risk is from each hazard, and now we have to figure out, all right, we know this is a risky thing. What's our plan? Now there are 4 options for this. You can accept the risk. If the risk is low, maybe you just say, well, it provides a lot of benefit. The harm is no big deal. It's low risk. It's probably not going to happen. And if it does happen, it's no big deal. We're just going to accept it. We're just tell the user, be a little careful. It'll be fine. Maybe we transfer the risk. One thing you can do with extremely high risks that are more than you can bear is you buy insurance. That's why we have insurance on our houses and our cars and so on, because the loss event could be very costly, but it's low frequency, and we handle that by buying insurance. The other thing you can do is blame the user. You can say, well, the manual said you have a nail, and if you didn't put a nail in, it's your own fault, and that's our risk mitigation procedure, is to blame the user. So you can transfer the risk onto other parties in various ways. You can also avoid the risk. So maybe don't have a person holding a nail with a robot around swinging a hammer. Maybe that's your plan, right? So you can avoid the risk. But let's say that in this case, yeah, you really need to have the person hold the nail, and you really need to do something about these risks. So then you reduce the risk. The most important part of safety engineering, the most impactful part of safety engineering, is making the decision to accept, transfer, and avoid, and not reduce risks unless you really have to. But what everyone talks about for safety engineering is the reducing the risk, because that's where all the effort is. But really, all the big mistakes are made on deciding accept, transfer, or avoid, or reduce. Getting that wrong is where all the big mistakes are made. After you've done that decision, then the rest of it is grinding through the safety engineering process, which we'll get onto. So reducing is you use technical mitigation for risk. What I mean by technical is there's a line of code, there's a piece of hardware, it's a technology approach to mitigating the risks. And for example, you might have hard limits on motion. So let's get to that. So at this point on, we're going to talk about reducing the risk as risk mitigation. The first step of reducing the risks of risk mitigation is you come up with a safety concept, all right? So you say you want to mitigate the unavoidable risks. And the key concept for safety engineering, the most important part of this part of safety engineering, is that the mitigation effort is proportional to the risk. If you have a high risk, you spend a lot of effort and time and resources and hardware on reducing the risk. And if it's a low risk, you spend, well, you try and get it right, but yeah, the risk was low, so it's no big deal. So the mitigation effort is proportional to the amount of risk. As part of this, let's assume it's moderate to high risk. You create a safety concept. For example, if you're worried about smashing fingers, one of the safety concepts is to limit the hammer force so that even if it does hit the hand, it can't smash it flat. And the other one is we're going to limit the first strike depth so that even if things go wrong, the hammer is not coming all the way down to the board because there's fingers in the way. So you add some safety concepts of some guardrails to say, well, even if something does go wrong, if we enforce these guardrails, it's going to limit the harm and take it from a high risk to a low risk by, for example, limiting severity or limiting the probability it will happen. And we might also detect out of position hand. We might stop the strike if there's no nail resistance. So you create some concepts of here's ideas to take this thing that used to be pretty dangerous and make it less dangerous, responsive to the hazards we've identified. You could also instruct the user to wear thick gloves, which then transfers the risk onto the user for not wearing thick gloves. And there's a bunch of ways to do this, and I'm not here to tell you what's wrong or right. I mean, I think wearing gloves is probably a good idea, even if the robot's supposed to be safe. But there you go. You have a bunch of safety concepts. Some of them involve hardware, some involve software, some involve operational procedures. It's all fine. It's a package deal. Then you do safety requirements. So after you have the concept, you have requirements. So each concept you say, well, I want to limit the force. Well, how exactly do I do that? So you go from a product level safety concept down to an engineering requirement saying, all right, in order to implement that concept, here's our safety requirements. And so they implement the safety concepts, and later on you're going to validate the safety requirements are met by normal engineering tests and validation procedures. So some examples, you may say, well, we're going to limit the hammer's force on the first strike to less than some number of newtons because we've looked at a lot of nails, we've looked at a lot of wood, and if the strike force is so many newtons, we're probably going to hit our initial strike, and we're unlikely to go all the way into the wood. And we can also say the first strike ends so many millimeters from the surface, so even though we limit the force of the strike, it might still go in too much if the wood is really soft. And so we're going to have a hard limit that when the hammer gets so close to the surface, it's going to hit a mechanical stop. It may be hard in the equipment. It shouldn't happen often, but that way we know there'll be enough room for fingers even if the nail goes in more easily than expected. And we may also have an emergency motion stop if you see less than a certain amount of force within the first few millimeters of nail travel. That's going to be fast reaction. That's going to be a lot harder to build. But you're going to pick some examples like this, and you're going to come up with a set of requirements that implements all the safety concepts. So what we've done is we've transformed from, well, we're worried about something and how bad is it, to engineering requirements that look like all other engineering requirements, except these are safety requirements because they don't trace to the user and product utility, they trace to the safety concepts. That's what makes them safety requirements. Now we're going to build, validate, and monitor, but we're thinking about the safety requirements, which is going to happen in parallel with the regular functionality requirements. We have to implement those mitigation mechanisms that we just did requirements for. And that means not only do they have to work, but there have to be no systematic faults, such as hardware or software defects that cause a misbehavior that violates the requirement that, no, really, this has to work. And it has to withstand random faults. We may have to use redundancy for that. Single event upsets are a thing. Sometimes you add 2 and 2 and get 5, and that was just the hardware just decided not to behave that way because that got hit by a high energy particle. That stuff happens. And so when you're up in the life critical safety area, you have to really worry about all sorts of things, really crazy things going wrong. But even for low severity things, low risk things, if there's a switch, if there's a limit switches eventually fail. So you have to ask the questions about what can go wrong to compromise the ability of those mitigation mechanisms to work properly. You have to do validation. You have to make sure all the safety requirements are satisfied, and you have to test the mitigation effectiveness. So this is an interesting thing. When you're testing for safety, you're not testing to see if the product works. You're testing to see if something goes wrong, does the product successfully deal with that? For example, on a microwave oven, there's a switch to turn off the oven when you open the door. Well, the first thing you do when you test mitigation effectiveness is you run the microwave, you open the door, and you see if it really works. If it doesn't work, you got a problem. There are other issues you have to deal with. Well, what if that switch gets stuck? Does it then keep running when it's open? And that gets back into the systematic and the random faults. You have to also validate the design process was followed. So safety engineering and testing is not just about, well, it passed the test, it's good. You also need to know that the engineering was performed rigorously enough that there's no reason to believe there's faults hiding inside the system that will defeat the safety functionality. And you need to monitor it in the field. You need field engineering feedback for incidents. Hey, we got 17 reports of microwaves staying on with the door open. We better look into that and find out what's going on before someone gets really hurt by that. And you have to ensure the mitigations keep working over the life of the product. We've been through a safety engineering workflow, but let me summarize it so that the pieces all make sense. The first thing is you do hazard identification. The next thing you do risk analysis based on the hazards for each hazard. How risky is it? High, medium, low. Then you do a risk mitigation strategy. So what are we going to do to mitigate these risks? And you come up with safety concepts. So the idea is we're going to limit force, okay, and what does that mean? You end up with safety requirements. And you may mix and match these steps, but the flow is you go from the hazard identification to the risk analysis, and you come up with a way to limit the risk, and then you come up with engineering requirements that implement that way you came up with. You implement them, you validate that they really work the way they're supposed to, and you do life cycle monitoring of incidents. That's safety engineering in a nutshell. Now there's some pieces I kind of skipped over, so let me go back and look at some of the topics that are involved in safety engineering as you go through this workflow. There are standards. There are international standards written by industry for how to do safety engineering, and they range in size from a small number of pages to more than 1,000 pages. And I'm not here to go through all 1,000 pages, but they all follow these same ideas. So a functional safety standard says there's a safety function that mitigates the risk. And that's what we've been talking about. A switch that opens and shuts down your microwave when you open the door, that's a safety function. It's the shutdown function. A hard limit that prevents a hammer from going further than it should, it's a safety function. So it's some sort of equipment or operational fault that triggers a safety shutdown. That's functional safety. Now there are more complicated types of safety we'll touch on briefly, but most of safety engineering is about functional safety. So functional safety assigns a thing called a safety integrity level, SIL, or the automotive guys use automotive SIL, ASIL, based on risk. And so most standards do SIL 1, 2, 3, 4, where SIL 1 is low risk and SIL 4 is high risk, and so there's 4 degrees of risk. Automotive does ASIL, A, B, C, D, but the ASIL D, which is their highest risk, lines up more with SIL 3 than SIL 4 for various reasons. And so what do we mean by SIL? Safety integrity level, yeah, that's nice, but what does it really mean? Okay, what it really means is 3 things all at once. And so this gets a little bit tangled up, but it means 3 things at once. The first is the risk from an unmitigated fault. Well, that's how we got here. The risk table coughs up SIL. So instead of high, medium, low risk, you just say high risk. Okay, well, that's SIL 4, or it's ASIL D. So the risk table coughs up the SILs, simplifying, but that's how it works out. So it means that at first. But, well, now you know it's high risk. What's your plan? Well, you don't want the high risks to happen unmitigated very often. So if you have a hammer that's going to smash someone's fingers, it's high risk, and that translates into it has to be extremely rare. It will never be 0, but it'll be extremely rare. And in industrial strength safety standards, you see numbers like 1 per 10,000 hours, 1 per 100,000 hours, 1 per billion hours, depending on what severe means and what the application area is. So how often unmitigated faults are allowed it corresponds to the SIL. So you can put a number. In some standards, they actually put a number, and the range and the increment between them varies depending on the application domain. There's also the engineering rigor applied to mitigation. That also goes with a SIL. So a SIL is the risk if you don't mitigate the fault. A SIL is how often it's allowed to happen without the mitigation. So how reliable does your mitigation need to be is the inverse of that. And it's also the engineering rigor. The idea here is the more risk there is, the more work you have to do to prevent it, and the less often it's allowed to happen. So SIL means all three things at once. Functional safety standards describe a safety process. Here are all the steps. I just outlined a bunch of steps, but they go into a lot more detail and say this is how you do it, this is how you do it, this is how you do it for each one of those steps, and the required engineering rigor based on the SIL. So they have a thing we'll get to in a minute about tables of different processes. And so you have to do these activities, you have to produce artifacts, which is a fancy way of saying work products or pieces of paper. That's it. Safety standards just lay out the process to do the risk analysis and implement the SILs based on your particular domain. Okay, so code quality and safety. This is one of the pieces in the safety standards. It's the one we all think about. There are hazards due to software defects. One of the reasons the robot arm may misbehave is there's a software defect. There also might be environmental conditions you have to deal with. But all it boils down to, for functional safety, you have a bunch of requirements, and did the software properly implement the requirements? You could have incorrect computational results. You could have the implementation does not meet the requirements. And the standards require code quality measures. So their countermeasure for hazards due to software defects is they require things like peer review and static analysis and test coverage and avoiding unsafe language features. So Mr. C, for those of you who have heard of it, that's where this comes in. Mr. C doesn't make you safe. It's a particular subset of the C programming language to avoid all the scary or ill-defined parts of the language. It doesn't prove you're safe. What it does is it helps you mitigate the risk presented by hazards due to software defects. So it plays a role, but it's a very precise role. Okay, and typically what you see is higher SILs or ASILs require higher code integrity. At the top SIL or ASIL, you want near perfect software. For practical purposes, it has to be perfect because any software defect is a chance for the system to misbehave, making it unsafe. But it's not a substitute for hazard analysis. Having perfect code doesn't make you safe because if you haven't done the safety engineering, you may have code that is perfectly unsafe. It does the same unsafe thing every single time because you engineered it in a way that didn't think about the hazards. So near perfect software is great, but it's a countermeasure. It's a risk mitigation approach for hazards. It's not safety on its own. I've mentioned engineering rigor several times, but that can be kind of a fuzzy concept unless you make it really concrete with examples. So here's an example to explain how safety standards specify engineering rigor. They usually do it with a bunch of tables. And the tables say, at a particular SIL or ASIL, here are the engineering processes and engineering work products you need to produce to make sure you've done enough work to mitigate risks. So here's a list of activities. Warning-free compilation conforms to Mr. C, and so on. And let's look at how this lines up for different SILs. At SIL 1, which is the least amount of engineering rigor that's still safety critical, you might be required to do warning-free compilation with a certain warning profile. You might be required to do informal peer reviews, and you might be required to have some sort of computer self-test so that if there's some sort of hardware defect in the CPU, it gets noticed on power-up. SIL 1 is low risk, so you need to do the bare minimum of safety, but not a lot. And so if your product is only low risk, the safety standard requirements are really not that onerous. At SIL 2, there's more risk, and that requires more engineering rigor. So not only do you have to do warning-free compilation, but you also have to conform to Mr. C, and probably you have a tool that checks the Mr. C for conformance to save yourself some work. And the peer reviews and the computer self-tests stay the same. What you typically see in a safety standard is the difference between SIL 2 and SIL 3 is quite large. SIL 2, it's medium-low risk, probably no one dies. There might be some injuries. SIL 3, much higher risk of a fatality. And these are very general statements. It all depends on the safety standard. But what you often see is a very big jump from SIL 2 to SIL 3 because SIL 3 tends to be more aligned with fatalities as a severity. So you have to really pay a lot more attention to engineering rigor. So you might have to do comprehensive static analysis with a tool well beyond just compiler warnings and conformance to a standard. And you may be told informal peer reviews, no, not good enough. You have to do Fagan-style peer inspections, code walkthroughs, because people can die. You have to take code quality a lot more seriously. And you may need to do redundant computers because up at SIL 3, you worry about, well, what if the computer fails while the equipment's operating and generates a bad answer? You need a second computer there to do something. We'll get into those patterns in a moment. And SIL 4 is basically have to do all the things except the things that are a bad idea for high integrity systems. So when you do the risk analysis, you do the hazard identification, you do the risk analysis, the risks come up with SILs, and then you go into the safety standard and find out for your piece of equipment, well, at that SIL, here are all the engineering steps I have to do. So the engineering rigor is very concretely specified by the safety standard. Now, I mentioned safety standards a couple times. Here's some examples of them. There's IEC 61508, which is a generic functional safety standard, and that has been adapted to chemical process, to rail, some others. There's ISO 26262, which started sort of in the 61508 land. They have some common heritage, but they use ASILs instead of SILs, and so it's at this point it's kind of its own thing. But all of these use risk tables, and it's just a question of different tables and different requirements for the SILs and different expectations for failure rates. They all basically go down very similar paths like the one I've been discussing. There's IEC 6730 for appliances, which is a much lighter weight standard, but it still has all the same ideas in it. And all these standards will have some different take on what the risk table is. Here's another hypothetical. This is a 5x5 risk table. Every standard will tell you what the risk table looks like, and you just go to the standard and say, okay, that's the risk table we're going to use. It's customized in how much risk is permissible. It's customized on what the cut lines are between different levels of risk, and it's customized with the risk engineering activity tables. Now, there are a couple issues that make safety really challenging, so let's talk about them. The first one is, what do you do about low probability? Safety is all about the bad days. People like to say, oh, look at my car, it saved me from a crash. We didn't crash today, and we didn't crash the next day. It's a great car. But in fact, safety isn't really about that, because safety is about the bad outcomes, not the good outcomes. That's not something people want to hear, but it's true. We operated a chemical plant today and it did not catch on fire is not a news headline. That's not how it works. But let's look at that a little more rigorously. Let's say you have 99,999,998 fatality-free miles versus 99,999,999 fatality-free miles. Well, the only difference is down in the last digit. They sound sort of the same if you look at the good days. But if you look at the bad days, that's double the fatality rate. So safety doesn't care about the good days, it cares about the bad days, because you have very, very low probability of adverse events if you're a safe system, and the changes in the number of adverse events are what matter, not the good days. It's about the bad days. Along with this, engineering intuition about plausibility suspect. People are astonishingly bad about thinking about rare events. They say, well, that'll just never happen. But what they mean is they haven't seen it, or they haven't seen it recently. And so things like lightning strikes and power outages and complex failures happen very infrequently in the real world. And so engineers tend to say, well, it didn't happen to me, so it doesn't matter. And it's amazing how the older you get, the more to safety you pay attention, because more bad stuff has happened to you. It's just a matter of exposure. You live long enough, you see a lot of crazy things. When you're young, you don't really see them. So it's hard, especially when you're new in your career, to really give credence to the rare things that are high severity. There are unreproducible incidents. It didn't mean it didn't happen. It just means it's hard to reproduce, but someone still could have died from that. And there's large fleet sizes. The simple way to look at the numbers is if you have something that's never going to happen to one car because it's a 1 in a million shot. Well, if you have 1 million cars, that's really going to happen every day. And so the tyranny of the low probabilities times the high numbers is really tough. That's what drives a lot of safety engineering in the real world. Security attacks also matter. One way of looking at this is that a security attacker, their job is to compromise the safety engineering assumptions. So as a safety engineer, you made an assumption that something was low probability. It was probably not going to happen. Well, a security attacker defeats you by saying, well, we're going to make sure that happens all the time. Oh, it's like, yeah, I know that wouldn't happen by chance often, but we're here to make sure it happens every day, and they're going to compromise your safety that way. There's certainly more to security than that, but the way security hits safety is by compromising all the assumptions, stated and unstated, that were in the analysis of the safety engineering. Let's talk about redundancy and safety. One of the things we know is that for really life-critical things, you end up with redundancy. But let's talk about why that is and how that works. If you're on a commercial jet aircraft, you really want to have two engines. And the reason is every once in a while an engine explodes or does an in-flight shutdown. This is a photograph of an engine that had a catastrophic failure, but the remarkable thing is the aircraft landed just fine. All the passengers are fine because the safety engineers had spent a lot of time getting this right. So even for things less dramatic than an aircraft, you often need two components in case one fails. And we're going to get to the specific patterns in a moment. The computer systems can fail, hardware components fail, software tasks crash, things break. Not all the time, but often enough that for life-critical tasks, when someone's going to die, you have to make sure, even if any component in your system fails, you have a backup plan. There's also silent data corruption. Sometimes a number just changes for no discernible reason. I mean, there are physical reasons, but the numbers just change, and you have to be able to survive a single bad computation in a life-critical system, and you do that through redundancy. So you need redundancy to detect failures. One type of redundancy is data coding, so CRCs, checksum, severity. Guess what? When you send a message down a network, you don't always get the same message out the other end. And so we take for granted that any communication network needs CRCs and checksums and parities. But for safety critical computation, you also need to protect your computer memory in a similar way because those bits occasionally flip. And you may need multiple computational elements. You have an adder, and 2 plus 2 equals 4, and 2 plus 2 equals 4, and once in a great while, 2 plus 2 equals 5. So you have to have some way of checking and detecting that that happened. There are two key redundancy patterns you see in numerous variations used all over the place, but it usually boils down to these two patterns. Everything's variation on these themes. The first redundancy pattern is a failover. So there's a primary computer or primary sensor or primary whatever, but there's a primary computer, and when it fails, you trigger over to a backup computer. The other redundancy pattern you see is a fail silent system component. This is a little less obvious, but is the core building block for all life-critical computing. There's two channels, two computers, and they do cross-checks. So one computer adds 2 and 2 and gets 4. The other computer adds 2 and 2 and gets 5, and they say, what'd you get? I got 4, I got 5. Now, you don't know which one is right. All you know is that they disagree, so the whole thing shuts down saying, I've just had a computational fault. I hope the system level has a plan, but I'm just shutting down because I would rather shut down clean than give a wrong answer. Now, these patterns can be nested. So the primary backup, the primary might be this two-channel cross-check, and the backup might also be this two-channel cross-check, so that the primary knows when it fails because its cross-check fails and it shuts down, and then the backup can take over. And rail switches are built that way, for example. These are real patterns you see in the real world. There's a pitfall here that people try and talk themselves into using less redundancy than they really need. So they may double spend a redundant component. As an example, you may have the cross-check pattern and say I have two computers, and if one fails, we'll just turn off the bad one. Well, how do you know which one's the bad one? One said 2 and 2 is 4, one said 2 and 2 is 5, but you don't know the right answer in the moment because they're arbitrary numbers. All you know is they disagree. How do you figure out which one's right? And so you actually need a third computer to break the tie, and so on. So there's lots of complicated patterns you can build, but you have to make sure that you never trick yourself into using less redundancy than you really need. A core principle of life-critical systems is no single point failure, because all components break, and they tend to break more frequently than we would really like to have fatal mishaps. So if you have a computer-based system where someone can die, you cannot have single point failures. Life-critical systems must cope with any component failing. You use redundancy to detect the faults and, if necessary, either shut down or have a backup plan to keep operating. You have to assume that any single component failure fails not just I'm going to die and stop working. You have to assume it creates an incorrect output and it's basically trying to kill you. So this is why we have the cross-check pair. One of them tries to kill you and the other one says, I didn't get that answer, and they shut down instead of having the dangerous output go out. This results in a fail-silent strategy. So the basic functional safety building block is fail-silent. It's the cross-check pattern I showed you that says we're going to make sure that if there's a computational error, the function just disables itself and some higher system level thing takes over. This is classic in automotive. Most safety functions, they function, but if something goes wrong, you get a little warning light and it just shuts off and the driver compensates for it. That's true of cruise control. It's true of a lot of different driver assistance features. And as far as that goes, that's great. You have to make sure the driver really can control the vehicle, but the driver's your backup plan. And so for most of safety, that works, just shutting down if something's wrong, but knowing you shut down instead of having a bad computation result is good enough for most safety. There are some cases where you have to fail operational. Airplanes have to keep flying. If a car is doing 100 kilometers per hour down a highway, it's not going to stop instantly, and so you need some residual functionality. That fail operational strategy could be fall back to a human operator, but in a purely computer-controlled system, you actually need a backup computer. So when the first component fails silent, the backup computer takes over. So you need extra redundancy for working even after a failure. That's a much harder thing to pull off, but in the self-driving car world, that's what we see the car manufacturers have to deal with, which is different than traditional cars because there's no human driver to be the backup anymore. You need to avoid common cause failures. It's not just a single component fails and causes a problem. You can have multiple failures that are correlated. So you could have two copies of a hardware component that both have the same software and that software has the same defect, and that's going to be a problem. That's a common cause failure. You could have one power supply that feeds two different chips. Well, you have two chips, but if you lose power, they both go. Or you could have a connector or other communications failure. So there's two independent signals on the same connector, and the connector comes loose, you've just lost both signals. So when you're doing system level safety engineering, the first thing you do is you say there's no single point failures. But the next thing you do is you look for common cause failures that amount to a single point failure. It's a single cause causing a bunch of correlated failures. And so the full statement is a life critical system shall have no single point failures and shall also have no plausible common cause failures. Another safety challenge is high severity. Now recall that we said risk was frequency times severity, and that amounts to an insurance risk computation. It boils risk down to the amount of dollars you have to pay out in the event of a loss. And you just take the average risk per operating hour, you take the average profit per operating hour, and if the profit's greater than the risk, you can make money. That's where that goes. But there's a problem with low probability times catastrophic severity. What's near zero times infinity? And those are problematic because if the catastrophic outcome is really severe, even a very low probability can have high risk, and you're almost always really guessing about the probability. We've seen this be a problem for hurricanes, for nuclear power mishaps, and so on, where the amount of damage is just huge, and people are kind of guessing about how often it happens, saying that, well, it'll probably never happen, so we're going to pretend it never happens, does not really work in practice because things have a way of going wrong. So that's why we have this question mark on the risk table. Low frequency times high severity is a difficult problem, and it's not a mathematical probability calculation. It's much more a risk tolerance question and a social acceptance question. So what do you do about the question marks? Well, it depends on the industry. It often relates to the likely news coverage of the mishap. Airplane crashes, hurricanes, nuclear power makes news. Individual car crashes, not so much. And in somebody's solar power system catching fire, probably not national news. So what you tend to see is that if the severity is extremely high and it's newsworthy, that low frequency, high severity rounds up to high risk treatment. And you tend to see that if the newsworthiness and the size of the loss, well, it's severe, someone died, but it's only one person and it's something we've become accustomed to, that often rounds down to like a medium or even a low risk. So it depends on the application domain, it depends on your system. But one question to ask when you're doing safety critical systems is, if I have low frequency, high severity, what's my risk really? And it's not an easy answer. It's something you really have to think about. Let's talk about safety culture. So safety culture is this nice word. It sounds good, but what does it really mean? Well, it's about two things. It's about, first, that you can identify and tell people about safety problems without reprisal. So if you have a good safety culture, you can find a safety problem that no one really thought of before, and it could be an unidentified hazard that you just figured out, or it could be a test failure that people just don't want to pay attention to, and you can say, hey guys, this is a problem. We have to deal with this. And you can know that you will not be fired, you will not get a bad job appraisal, you will not lose out on the next merit raise and all those things. You can know that it's a safe space to say, we have a problem. That's the first half of good safety culture. The second half of good safety culture is you can trust your management to actually do something to mitigate the risk. Now, sometimes they may say, yeah, we knew about that hazard and we've done our risk mitigation. We've decided that we're going to accept that risk. And at that point, you've done your job and they've done their job. You may philosophically agree or disagree with their decision to accept their risk transfer, but you have a positive safety culture in that all the pieces are working. Where the safety culture gets to be a problem is that people don't listen to hazards, or they retaliate against someone who points out a hazard, or they deviate from the safety standard and say, yeah, the book says this is supposed to be high risk, but we have to ship, so we're going to call it low risk. Those are signs of a problem with safety culture. So you should expect that you can point out safety problems, and you should expect that management will make a good faith effort to mitigate them to the degree that that makes sense. And if you have that, you have all the makings of a good safety culture. Now, I have a pie chart of the different amounts of efforts that are spent on safety, and this is not the talk where I'm going to go through how I got all these numbers. These are based on an industry benchmarking survey, but the part I want to point out is the safety engineering and system engineering. What we've seen across many organizations, across several industries, is that system and safety engineering together are about 10% of the total project effort, all the way from writing requirements out to finishing testing and shipping. And safety is about 2.5%, and system is 7.5%. So if you have a 100-person team, you want 2.5 people doing safety, and you want 7.5 people doing system engineering. These tasks are often understaffed, and if they're understaffed, you're going to have a safety problem that probably manifests as a safety culture issue. You need independent oversight required for project sign-off. Another question to ask is, we have the safety engineers, but the person whose bonus depends on shipping on time is the one who decides if it's safe enough. That's dysfunctional. You need a system in which the person who is supposed to say yes does not have incentives to say yes when they shouldn't, and is not afraid of being punished for saying no. Wrapping up, here's some key safety engineering ideas. Testing does not prove safety. You don't get safety by testing, you get safety by doing safety engineering, and testing is just a piece of that. You do hazard and risk analysis, you identify the hazards, you rank them based on risk, and then you mitigate the risks, avoiding common cause failure risks, and making sure you have ultra high quality software if it's a life critical system to mitigate the hazards from software defects. You use engineering process rigor. So safety engineering is all about finding out what can go wrong, what the risk presented is, and then applying engineering process rigor to resolve the risks. Some of them are engineering techniques, engineering effort. Some of them are applying redundancy where it's needed. The safety standards help provide guidelines on what amount of engineering rigor is appropriate and what techniques are recommended. And you need a safety culture to make this work. I'll wrap this up with a meme about safety first culture and governance.